All right, everyone, here's our applications of work video. So, we have already talked about work, right? Work has kind of two definitions. The first and primary definition is the change in energy. The second definition, and this is how we can draw forces into energy, is we can change something's energy by applying a force to it across a displacement. So, we have this F, and this is F parallel D, the force that is parallel to the displacement. When we get into second semester, we're going to look at this other half of the equation with FD cosine theta. But that is second semester. We're not going to worry about that yet. We're just going to go with the part of the force that is parallel to displacement. Okay, notice though how energy plus or minus work is equal to energy final. So we just have to decide, is this positive work or is this negative work? But that's same thing as we did the first part of looking at work. All right, let's take a look at our applications of work class problems. Um, Maybe if I get to the right page. Here we go. Okay, applications of work. One that we can do is have a force versus distance graph or force versus displacement graph. So this one we're looking at a a bow pulling back the string for a bow and arrow. So the further we pull this string back, the more force it takes. When we pull it back 0.6 meters, it takes 400 newtons as opposed to half that is 200. How much work is needed to pull back the bowstring? Well, bows, we don't know how to have, right, change in energy is work. We don't know how to calculate the energy of a bow based on its displacement because it's not one of our three major types, so we can't use that definition. So work, in this case, we're going to have to use force displacement. And remember, it's just the part of the force that is parallel to the displacement, which, if we draw ourselves a little picture, right, here's our bow when it starts, we would have to exert a force backward. And which way would the displacement of this string go? Also backward, so that is completely parallel. They're in the same direction. Okay, but the force changes over time. Force changes over time, so how do we calculate this? Well, let's take an analogy from a VT graph. Let's say I have a VT graph. If I want to find displacement, how would I do this? I would take the area of a VT graph. Why? Because, well, velocity is displacement over time. So if I want to find displacement, I would rearrange that to do displacement is velocity times time. This is the y-axis, this is the x-axis, and when we multiply things together, we get the area. So that would be how we'd calculate displacement given velocity and time. If I want to take a graph that is force displacement, right, I'm trying to calculate work, which is force times displacement. That's the y-axis, that's the x-axis. How do we multiply those together? We take the area. So we're going to take the area of this nice triangle here. That gives us work. So area 1/2 base times height. So our work will be, let's see, base is 0.6, height is 400 over 2. If we plug this into our calculator, we get 120 units of any sort of energy, joules. All right, so that's how much work is pulled back, or how much work is needed to pull the bowstring back. We're now looking at if this bow shoots a 100-gram arrow, how fast will the arrow be shot? Well, in pulling this string back, what type of energy have we given this? We've given it potential energy, and we don't know really how to calculate that. So I'm just going to say of the bow, but we know how much we've put in. We know how much we've changed the energy by, so we know that number. Okay, so energy initial plus work equals energy final. Well, we didn't have any energy to start. Right? I guess first, why did I say plus? Why did I say plus work? It's because we're giving this bow energy. We're not taking it away. We're giving this bow some energy. Okay, we didn't have energy to start. It was just a bow sitting at rest. But then we added in 120 joules of work to get energy final. And what did we do with that energy final? We let the bow go to transform that into kinetic energy of the arrow. Okay, so we know that 120 joules is going to equal 1/2 mv squared. Okay, so 120 is 1/2. 100 grams is 0.1 kilograms. And then velocity is what we're trying to find. So v squared, let's see, that would be 240 divided by 0.1, so 2,400. If I'm doing my mental math right, but I'll check myself here. Times 2 over 0.1. Yes, 2,400. And then take the square root of that. We get our velocity would be 48, or to 3 sig figs, I guess, 49.0 meters per second is velocity. All right, we started with nothing, and then we put in work, and then it comes out as kinetic energy final, because that's how we release the arrow. Okay, next problem. 70 kilogram cyclist is on top of an 80-meter tall hill. Hill is a length of 12.5 meters. Or I'm sorry, 8-meter tall. 8-meter tall hill has a length of 12.5 meters. He reaches the bottom of the hill at 18.2. There's our cyclist. Whee! Happy. He's got a helmet on. Don't worry. Okay, so there's our cyclist. He has a velocity of 18.2 meters per second at the bottom. So I'm going to call that final because that's at the bottom. And he starts, I should say, I apologize. I should say starts at rest. Starts at rest. That is something the problem should include. He starts at rest on top of an 8-meter tall hill. Okay. So we've got our cyclist starting at V initial is equal to 0. V naught equals 0. With how much force did the cyclist pedal down the hill? All right, well, we're looking at force. We're looking at relating heights and velocities. That can only mean one thing. Energy initial plus or minus work is equal to energy final. Are we putting energy in or taking energy out? Well, the cyclist is pedaling, so we're putting energy in plus work. All right, it starts with gravitational plus the work of the pedaling, and then energy final gets kinetic at the end. Okay, gravitational MGH work. We're going to have to use our force and our displacement. Let's just make sure that that they're parallel. All the force, he's pushing himself forward, but then the displacement, he is moving forward. So there we go. Okay, so those are parallel. And then kinetic energy, 1/2 mv squared. And we are looking for the force with which he pedaled. So we should have everything else. Let's see if we do. 70 kilogram cyclist. G is at 10. H, the hill is 8 meters tall. Plus, we don't know force displacement. He moves 12.5 meters because that's the length of the hill. Is equal to 1/2 70 kilograms. We know he ends at 18.2 meters per second, and that gets squared. Okay. So 70 times 10 times 8. So we get, and I'll bump this over here, 5,600 plus 12.5 times the force is equal to 1/2 70, 18.2 squared. 1,600 to 3 sig figs. Okay. So then I'd get 12.5 times the force is equal to 100 minus 5,600, 6,000. So our force, divide that by 12.5. We have a force of 480 newtons. All right, so that's our pedaling force. right? We recognized we have an energy initial with gravitational. Then we put in some work with the pedaling, and we end at the bottom of the hill, but moving faster than we would have been moving had we just rolled or had we just let ourselves go. All right, number 3, John pushes a crate across the floor with different surfaces. He has to push with different forces for the different surfaces. Pushes with 20 newtons for 5 meters. 5 meters, 20 newtons. Then pushes with 35 newtons for 12 meters. Okay, so 35 newtons, 12 meters. Then 10 newtons for 8 meters. 10 newtons for 8 meters. How much work does John do? Well, we could say that over this first stretch of time, John does work equal to force times displacement. We could say over the next stretch of time, oh, I apologize. Click to the next page. 2 pages, actually. The next stretch of time, here we are, John does that much work, force displacement, and then here he changes the energy by force displacement. So we could say 100 joules of work is done in the first part. In that second part, 35 times 12 gives us 420 joules of work in that second part. Here, 80 joules of work in the third part. So our total work total, we just add them all up together, we get 600 joules of work. Okay, so that's nothing groundbreaking, but it is important to realize that work is just an additive quantity. We just add it up together, and it's totally fine. Okay, moving on to the next page. 3 kilogram box down a 4 meter tall ramp. Okay, 4 meter tall ramp, 3 kilogram box. Box slides down 6.2 meters of the ramp. So down 6.2 meters of the ramp. Begins its descent with initial velocity of 5.8 meters per second, and it reaches the bottom traveling, so V final, 7.6 meters per second. What is the average force of kinetic friction? So force of friction is what we're looking for between the box and the surface. Okay, the normal force is 22.9 newtons. I had to give you the normal force because we haven't solved how to find normal force on an incline yet. And I think actually I'm not looking for force. I think I'm looking for coefficient. I think I'm looking for coefficient there. Otherwise, I wouldn't have needed to give you the normal force. So what is the average coefficient of kinetic friction? Okay. Well, we start with height and velocity. We end with no height and velocity. We know how far we've traveled, so we can set this up as energy initial. Work equals energy final. We have to figure out, is this plus or is this minus? Well, the force acting is friction, and friction always takes away, so it's minus. Okay, we start with both kinetic and gravitational potential energy, UG, minus work done by friction, and then energy final, we just end moving with some final amount of kinetic energy. Okay, 1/2 mv squared plus mgh minus force of friction displacement equal to kinetic 1/2 mv final squared. And this should be a v initial over there, sorry. Okay, let's plug in some numbers. 3, we start moving at 5.8. That gets squared plus m is 3g10, h 4 meters tall. Okay, minus force of friction. We don't know force of friction yet, but if we're looking for the coefficient, and I apologize, I should change that there, mu kinetic. If we're looking for the coefficient of friction, right, force of friction is equal to mu Fn when this is all kinetic stuff. So we can plug in mu k, and then we know the normal force. We know the normal force because it tells us is 22.9 newtons. K is equal to 1/2 mass of 3, v final of 7.6 squared. All right, let's do some multiplication here. 5.8 squared. First one, I get 50.46 plus 120 minus 22.9. Oh, I forgot the displacement here. I apologize. So in that displacement, sorry, pen's not wanting to work for me. There we go. Our displacement down the ramp, it travels down 6.2 meters of that ramp. Okay, 22.9 times 6.2. So this would be 142 essentially times mu kinetic is equal to, and then 1/2 times 3 times 7.6 squared, 86.64. Okay. So if we set this all up over here, I'm just going to bring this up. Okay. So we get 170.46 minus 142 mu k is equal to 86.64. All right, I'm just going to solve this from here. If you need to take another moment to solve this on your own, please feel free to do so. But I get coefficient of kinetic friction is 0.59. All right, there's our coefficient of kinetic friction. So we were able to take this and not just determine things about the forces and the displacement, but to look at what type of force it is and get information based on that type of force, especially when we're given a change in height and a change in velocity there. Okay, oh, there's another part here. After reaching the bottom, it now hits a spring on a flat surface. The spring compresses 0.42 meters to bring the box to a stop. What's the spring constant? Okay, well, in this case, we should just look at what type of energy, or not what type, how much energy does it have at the bottom of the ramp? And that's all its kinetic energy of that final. If we're done with the ramp, there's no more friction from that ramp, so we're on that flat surface. When it gets converted, right, E naught plus or minus work is equal to E final. However, there's no work in that case. So when this hits the spring, we just get kinetic energy because there's no outside forces. That's why there's no work. There's no outside forces. It's just the movement and the spring. The kinetic energy turns into spring potential energy. So we have kinetic energy of 86.64. We calculated 1/2 kx squared. So 86.64 is equal to 1/2 k. When we compress 0.42 meters, so 0.42 squared. Okay, 86.64 times 2 over 0.42 squared. We get a spring constant of 982 newtons per meter. All right. Moving on. Okay, we lift a 3.6 kilogram box up 1.2 meters. How much work do you do? Well, there's two ways to solve this problem. One is we could look at energy initial plus work equals energy final, plus or minus. We can say plus in this because we're lifting the box up. We're giving it that extra gravitational potential energy. We could say, so there's two ways to do this. We could say either we start with 0, so we look at plus work, and then we end with gravitational potential energy. So we could say work is mgh, mass is 3.6, g is 10, h is 1.2. So that would be a total work of 43.2 joules. We could do it that way. We could also say force times displacement, because our force is up, our displacement is up, and we are pushing up this box. To push something up, what force do we have to overcome? We have to overcome gravity. So if gravity is pushing down is mg for our weight, that'd be 36 newtons. We would have to push up to overcome gravity. So we could say 36 newtons pushing up force and then displacement, it moves up by 1.2 meters. Well, that would get us 43.2 joules of work also. Either way is perfectly fine. You pick whichever way works best for you in that case. Okay, a slightly similar problem. Lift up a 50 kilogram box, 0.8 meters, carry it horizontally, and then set it back down. How much work did we do? Okay, so lifting it up, we could say similar to what we just did before. We could say, right, energy initial plus work because we're giving it energy and lifting it up equals energy final. But we didn't start with anything, so work is just going to be mgh 50 10.8. All right, so our work in this case would be 400 joules just for lifting it up. Okay, carrying it horizontally. So this is where we have to remember that work is force, whatever force is parallel to displacement. Because if I have a box and I want to displace it horizontally, right, that's our displacement, I have to hold it vertically. So there's our force to prevent it from falling down. Are these parallel? No. Force is not parallel to displacement. So in this case, our work would be 0 joules because there is no force parallel to our displacement. So our work is actually 0. Okay. And then setting it down. How much work did we do here? Well, energy initial plus or minus work. Plus or minus work is equal to energy final. Well, it starts with gravitational potential energy and it ends with 0 energy. So that means it must be negative work. We must be taking work out, which makes sense. If we put work in to lift it up, we take work out to put it down. Okay, so in this case, mgh minus work is going to equal 0. Oh, so our work is just going to equal mgh again. Not 0, sorry, work. Work will just equal mgh. Well, it's the same mass, 50. It's the same g, 10. It's the same height of 0.8 meters. So our work in this case will be the exact same as what it was before. But we have done negative work. So this is 400 joules removed as opposed to the 400 joules we added previously. In total, right, the box starts on the ground. If we look at energy initial and energy final for the whole thing, the box starts on the ground. Energy initial plus or minus work equals energy final. Box starts on the ground, so that means an energy initial of 0. And the box ends on the ground, not moving, so an energy final of 0. So what must our work be? Work has to be 0 joules total. So I'll just do total there. Total work is 0 because we didn't really change its ending state from its beginning state. That's why I don't go to the gym. Because, right, you pick something up, you move it around, you put it back where you started. Your total displacement is 0, so your total work is 0. It didn't change the energy of it, so why would I work out if I'm not actually putting work in? All right, one more page for you here. Okay, 8 kilogram box at rest, position A. We push the box with 90 Newton force for a distance of 40 centimeters. Until we release it, the box then slides. Oh, I apologize. The picture says 60. The problem says 90. I'm going to trust the problem here. Problem says 90, so we're going to go with the problem's number. Okay, until we release it, position B, it slides along a horizontal table where the coefficient of friction is 0.25. Coefficient of kinetic friction is 0.25. Eventually, the box comes to a rest at position C. What is the box speed at position B? Okay, well, we can say energy initial plus work equals energy final. Why are we using energy for this? Because we know it's at rest. We know the force we push it with. We know how far it goes. If you're talking about velocities, heights, forces, and displacements, that is a great recipe for energy. Great recipe for energy. Okay, it starts at rest. This thing is it's at the same height the whole time, so no gravitational. So there's no initial energy. We are adding a force. We're giving it energy, so it's plus work. Energy final, well, it'll have that kinetic energy in that energy final there. So force displacement. And is this force parallel to the displacement? Well, force is pushing right. Displacement is happening right. So yes, they are parallel. 1/2 mv squared. All right, we push with 90 newtons over 40 centimeters, so 0.4 meters. 1/2 mass is 8. Velocity final is what we're looking for. So our velocity, let's find out. 90 times 0.4, okay, times 2 over 8. Take the square root of that number. We get 3 meters per second. Okay, there's our velocity at B. What is the distance between position B and position C in centimeters? Okay, distance between position B and C. Well, we know how much energy it has at position B. So I'm instead of initial and final, and I'm actually going to go back and relabel this here. I'm going to label this energy at A and energy at B. So then we can compare now energy at B plus or minus the work with energy at C. All right, well, now this work, are we in the frictional area? Are we taking work out or are we putting work in? Giving it extra energy or taking some of that energy away? We are taking it away because friction slows it down. Friction always takes energy away. So energy at B, we've got kinetic energy minus, and then the force and displacement. Parallel, well, force is to the left, displacement is to the right. Those arrows are parallel, but they're opposite directions, hence our negative sign. Energy at C, it comes back to rest at position C, which means we're back to no energy at all. Okay, so then we can say our kinetic energy is the force displacement, and this is our force of friction. So 1/2 mv squared. Frictional force, remember, we can express as mu Fn, mu kinetic Fn, because it's sliding, is mu k, times the displacement. Well, the only thing, we know mass, we know velocity at B. We're looking for mu. We're looking for D. We are given mu. The only thing we don't know yet is normal force, but we can find it out, right? Free body diagram. If we're looking at this box, it has normal force up, gravitational force down, frictional force holding it back. But for normal force, we can say, since the box isn't jumping up and down off the table, we can say that normal force must be equal to gravity, so mg. My apologies, mg. And we know this because the sum of the forces in the y-axis is 0. So normal force then would be 80 since we have a mass of 8 kilograms. All right. So 1/2 8. Its velocity at B we said was 3 meters per second. That gets squared. Mu k is 0.25. Normal force is 80 newtons. Oh, I forgot the newtons. Whoops. And then displacement, that's what we're looking for. So if we solve this question, okay, over 80, I get a displacement of 1.8 meters. 1.8 meters. All right, we are almost done. Almost done. Fill in the chart for the sign of the work between each position for each of the following systems. So from A to B, B to C, and A to C for this box. So the block only, we put in positive work. The person who pushes from A to B, we're giving it extra. The person who pushes the block, well, we are giving the energy to the box, so the person experiences negative work. Okay, the table providing the friction. Well, remember, the block or the table providing the friction, there's no friction between A and B, so this does 0. This does 0. The block and the person between A and B, well, the person gives the block its energy. So what the person loses, the block gains. So this will be a net 0. The table, now we throw in block, person, table. The table provides the friction, which there's no friction yet between A and B. So if we look at block and person, and then we add in the table, that's also going to be 0. And right, these are joules for all these zeros. Okay, B to C, this is where the friction happens, right? The block loses the energy that it gained previously. The person has no part in the friction, so that makes no impact on the person. The table that provides the friction, well, if the block loses the work, the table must gain that energy. And it'll see that as a form of like heat energy primarily. The block and the person only. Well, person is nothing. The block loses energy, so that'll overall be a loss. Block, person, and table. Okay, well, the block loses energy, but whatever it loses, it gives to the table. And then the person does not experience anything, so 0. Okay, and then from A to C, well, the block, it gains energy and then loses it again. Starts at rest, ends at rest. So the block will not experience any change. The person, well, the only thing that the person did was it gave energy to the block to begin with. So the person will have negative work over the course of this system. The table, it didn't give any energy away. All it did was gain that heat energy from slowing the block down. The block and the person, well, the block didn't change, but the person lost energy, right? We can take 0 and negative and just add those, combine those together. Negative work for the block and the person only. But then here, right, so whatever, the person gave the block energy. The block then gave that energy to the table in the form of heat. So the person lost some, the block had a net 0, but the table had a net gain. So overall, there is a net 0 for the block, person, table. Okay, this becomes very important in identifying what we call open systems and closed systems. What is an open system? An open system is any system that can gain or lose energy. So energy changes in an open system. To contrast with that, a closed energy or a closed system means energy is always conserved. Energy is always conserved. So if energy is always conserved, that means no work. It means always. Energy initial is equal to energy final. Energy changes, that means there is work. It can be positive or negative. It just means that there is a change in energy. So we can see the system with the block only. It experiences positive work and then negative work. So there are changes. So this is what we would call an open system. The person experiences a change in energy by giving it to the block. So that is also an open system. The table only. Well, through the first part, there's no change in energy. So that looks like it might be closed so far. But the second part, positive work, that table changed energy. So that's an open system. The block and the person only. Well, for this first part, whatever the person lost, the block gained. So that looks like a closed system so far, now that we're considering multiple objects. However, the second part, the block gave that energy then to the table, and the table is external to the system that I'm asking you to look at here. So there is a loss of energy. That is an open system. The block, the person, and the table. Now we have a closed system. This is something where the person gave its energy to the block, but then the block gave its energy to the table. So we have to consider all three of those for energy to always be conserved. Okay, so how can we tell an open system from a closed system? I'm going to say all energy gains and losses All energy gains and losses happen between the objects included in the system. All of the energy gains and losses happen, right? The energy transfers have to happen from one object to another that's in the system, and maybe from that object to yet another that's in the system. But for it to be closed, everything that happens must be included within the system for it to be closed. So I should say this is for closed systems. Another way that we can talk about this is for an open system. So then an open system, there are external forces is the fastest way to identify this. External forces. So when I look at the block and the person only, there is an external force being applied of friction. If I were to look at the block and the table only, there is an external force of the push from the person. External forces tell us that it's an open system, as opposed to the closed system where all of those energy transfers happen between those objects. So all forces are internal to the system and the objects that we're including. All right, I think I've rambled on long enough for this video. If you have any questions, please do let me know. But that's it for this one. Have a great day. We'll see you next time.